Hello everyone, I am Mr. Ashish Chaudhary, Assistant Professor of Mechanical Engineering Department of Vidya Prasarab Mandals, Maharishi Parshuram College of Engineering, Bhubaneswar. Today we are going to study a strength of material subject. In this, we are starting a chapter as a unidirectional, bidirectional and triaxial stresses on a metal body. Okay, first we'll see here as stress. What is stress? Stress is an internal phenomena when the force applied on the material. Okay, that means this is a resistance force inside of the material. When we applied some load external to that body, then resistance will be developed. That resist force will be available into the material. Okay. So here the definition of the stress as the ratio of applied force to the normal area, because we will apply the force on the body, so same amount of force will be generated from inside of the material. So that's why we can write down the definition of stress as a resisting force per unit area. This resisting force is equal to the applied force, so that's why we have the formula as the ratio of applied force to the normal area. So generally stress is denoted by letter sigma is equal to force upon area. It has SI unit is Newton per meter square, or we can calculate it is in Newton per mm square. Now next one as tensile stress. Okay. So for tensile stress we have considered here one bar of a cross sectional area A. On its longitudinal direction we have applied some load as a P, or the forces in pull direction. Then what will happen? Okay, so some resisting force will be available inside of this bar, and if you take a ratio of this resisting force to the cross sectional area, we will see as a tensile stress. Okay, but actually this resisting force is equal to the applied force. So that's why we have taken here the formula as the sigma or T is for tensile is equal to tensile force upon area. Why we call it here tensile? When we apply the force on this bar is going to elongate it. So that means tension will be created in this bar. So that's why we consider this stress as a tensile stress. So sigma T is equal to tensile force upon area. Now about the strain. Okay. So strain is the ratio of change in dimension to the original dimension. Generally strain is denoted by E, small letter E, is equal to, so change in dimension, if you see same example here, so change in dimension as here, when the force will be applied, tensile force will be applied, the bar will be elongated. So that means the length of this bar will be changed. So it will be increased. So it is increasing the bar is delta L. Okay. So delta L as a change in dimension. And what is the original dimension? So original dimension is length of bar. So here strain is equal to dl by L. So strain has no unit. Okay. Now next one. Now we'll see about the Young's modulus. So Young's modulus as when we will consider the stress versus strain diagram. Same figure we will consider. If you are applying the load on the bar, stress will be occur into the bar. When we apply the force, then there will be change in the dimension, that means strain will be developed. Okay, so if you are taking a ratio or taking a graph as stress versus strain, then what will happen? Okay, so this will be shown this curve. So here what will happen, up to some level this graph as a straight line, and after that there will be curves, and after there is a break point. Okay, so we will consider this is as a break point. In that the bar will be breaked. But if you consider this point is A, up to the point A, due to the elasticity, bar will be elongated. There is a change in shape. When we release this force, what will happen? Up to this point, the bar will be take its original shape and size. That means original length. Okay. So this is, so from origin to A, this is called as elasticity. when the material takes its original shape and size, that property is considered as elasticity. After the point A, when we increase the load and we release the load, there will be no regain of its original shape and size. That means this elongation or the change in dimension is permanent one. Okay, so this is called the plasticity. Okay, after that, when we increase this load, then this bar will be break at some point. Okay, so in that O to A, so first we will see about the point O to A. So in this we have generally a straight line curve. So in straight line curve, we will, if you suppose we find out the slope of this curve. So slope of this curve is the change in y direction or change in x direction of this graph. So change in y direction, we are taking a sigma stress up to this point, and change in x direction as a strain. So this is the slope. This slope will be constant one. Okay, so that's why this slope is the property of this material, and this property of material is generally, we will say, stress is directly proportional to strain from the point O to A. Okay, to remove this proportionality sign, if we will take slope, this E is equal to sigma upon E. So this slope is also called as Young's modulus or modulus of elasticity. So this is the property of material. Okay, so this is about the Young's modulus. So here we see the stress, tensile stress, strain, and then Young's modulus. Now we'll see as a Poisson's ratio. Same figure we have considered here. We have a bar with a length L, cross sectional area is A. Okay, suppose we apply the load, tensile load, then what will happen? Its length is going to increase. So strain will be developed. If you consider length will be increased, this is in longitudinal direction. That means this is axis. It is along the axis of the bar. So that's why this strain is called as longitudinal strain. That means this is the ratio of longitudinal strain as change in length to the original length. But when the force will be applied, tensile force will be applied, its cross-sectional area will be reduced. That means there is a change in diameter or the breadth and width. Suppose you consider a circular bar, then diameter is going to reduce and tensile force is applied. So diameter will be reduced and correspondingly area is going to reduce. If you consider it is a rectangular bar, rectangular cross-sectional bar, then its breadth and width is going to reduce. So correspondingly area is also going to reduce. Okay, so that's why when tensile force will be applied, its length will be increased but cross-sectional area will be decreased. Suppose we consider there is a compressive force, then compressive force, its area is going to increase. Its area is going to increase but length is going to decrease. Okay, so for that we have considered here the two strains. The first one is a longitudinal strain. It is along the axis of the bar. This is as a ratio of change in length divided by original length. And lateral strain, which is perpendicular to this axis of the bar. Lateral strain is equal to change in lateral dimension divided by original lateral dimension. Or you can say it is a change in cross-sectional area divided by original area. And suppose we have taken the ratio of lateral strain to the longitudinal strain. This ratio is considered as mu, or it is equal to 1 upon mu. This is called as Poisson's ratio. Okay, this is the Poisson's ratio. Poisson's ratio is denoted by the letter mu or 1 upon m. Poisson's ratio is equal to the lateral strain divided by longitudinal strain when the force will be applied on this bar. So here m has a value varying from 3 to 4. Okay, so that means the Poisson's ratio value is ranging from 0.25 to 0.33. Okay, so this is about the Poisson's ratio. Now we'll see the rectangular block subjected to the normal stresses on all its faces. For that, we have considered a rectangular block as A, B, C, D, E, F, G, H. Okay, and we have the directions of this bar are, this is X direction, Y direction and Z direction. That means AB, the distance is available in X direction, BF distance is available in Y direction, and BC distance is available in z direction. Okay, so here we have considered here AB is equal to x distance, BF is equal to y distance, and BC is equal to z distance in respective direction as x, y, z. Okay, in that along these distances and the directions, here this rectangular block is subjected with stresses. Okay, so in x direction the faces AEHD and BFGC are applied with the tensile stress as a sigma x. Okay, yeah. And the faces ABCD and EFGH, these are applied with, these faces applied with the tensile stress as sigma y. Okay. Similarly, the faces AEFB and DHGC are stresses with the z directional stresses as denoted by sigma z. Okay, sigma z. Okay, now we will see when the force will be applied, there will be some strains. So just we say in the x direction the AB distance will be elongated. Okay, just we see if you consider the y directional stress, then BF distance will be elongated. If you consider z directional stress, then the BC distance will be elongated. But correspondingly, when we apply sigma x directional stress, there will be reduced in BF and BC distance. Okay, that means when consider a axial direction, there will be elongation, but lateral direction there is a reducing dimensions. So correspondingly, we will see one by one what is the change in the strains. Okay, so here first we see strain of AB. Strain of AB is equal to strain along the x-axis. It is algebraic sum of the strains along the x-axis due to the stresses sigma x, sigma y, and sigma z. Okay, so due to the sigma x, AB distance will be elongated, but due to the sigma y, the AB distance will be reduced. Due to the sigma z, this AB distance will be reduced. Okay, so this is the total strain in distance AB or AF. This is the algebraic sum of the strain developed by stresses sigma x, sigma y, and sigma z. Okay, so here we have sigma x is equal to, there will be tensile action will be available into the AB, so that's why we have taken it is positive. It is by using a Young's modulus formula, the strain is equal to stress upon Young's modulus. So stress, so here E of x is equal to stress in x direction sigma x divided by E minus sigma y by ME. Why here minus taken? Because due to the application of sigma y, so distance AB will be reduced. So that's why there is a compressive stress will be developed, and that's why we are taking here the minus sign. So sigma y divided by ME. So similarly, if you consider the sigma z, the stress in z direction, then when we apply the stress in z direction, this AB distance or EF distance will be reduced. That is, compressive stress will be developed, and this is the minus sigma z by ME. So this is about the strain is available in x directional. Okay. Now next one, similarly, we will see the strain of BF is equal to EY. Okay. So BF distance. So BF distance of rectangular block, or BF is equal to AE is equal to DH is equal to GC. Okay. When stress is available in y direction, this distance will be elongated. But if you consider stresses in sigma x and sigma z, so this distance will be reduced to 1. So that's why we have the strain in y direction is equal to, so due to the stress in y direction, it is a tensile one, so that's why it is positive, sigma y divided by E minus sigma x divided by ME. So here 1 upon M we have considered as a Poisson's ratio, minus sigma z upon ME. Okay. Now next one. Similarly, we will see the strain of BC. So this is distance BC is available in Z direction. So in Z direction, when you consider a sigma Z, so there will be elongation in BC. But if you consider a sigma X and sigma Y, there is a reduce in the direction, reducing the dimension of the BC. So correspondingly, we will see here the strain of BC is equal to Ez. That means the strain in Z direction is equal to strain along the Z axis. So this is Ez is equal to sigma Z by E, because this is a tensile one, that's why it is positive, minus sigma X by Me. So this is minus because it is a compressive one, minus sigma Y by Me. So here we have the equation number 3. Okay. So now, by using the formula of strain, change in the length of AB is equal to E of X multiply with X, because original dimension of AB is X, multiply with X directional strain as E of X. So similarly, change in the length of BF is equal to E dot Y multiply with Y. Okay. Then change in length of BC is equal to E of Z multiply with Z. Now we will see the volumetric strain. So volumetric strain is denoted by EV. It is the ratio of change in volume divided by original volume of this body. So we have volumetric strain. Generally, it is algebraic sum of three directional strains, that is E of X plus E of Y plus E of Z. By using this equation, we will substitute values of E of X from 1, E of Y from 2, and E of Z from 3. Okay. So for that, we have E of Y is equal to sigma X by E minus sigma Y by Me minus sigma Z by Me plus sigma Y by E minus sigma X by Me minus sigma Z by Me plus sigma Z by E minus sigma X by Me minus sigma Y by Me. So here volumetric strain as, so we simplify this equation as sigma X by E plus sigma Y by E plus sigma Z by E minus 2 of sigma X by Me minus 2 sigma Y by Me minus 2 sigma Z by Me. Okay. So now after simplification of this equation, we will take it common from these 3 as 1 upon E. So 1 upon E in bracket sigma X plus sigma Y plus sigma Z, and from these 3's as minus 2 divided by Me in bracket sigma X plus sigma Y plus sigma Z. So taking common this sigma, addition of this stresses as sigma X plus sigma Y plus sigma Z multiply with in the bracket 1 upon E minus 2 by Me. Okay. So from that again we take it common 1 upon E as volumetric strain EV is equal to 1 upon E in bracket sigma X plus sigma Y plus sigma Z multiply with in bracket 1 minus 2 divided by M. So here if you see 1 upon M is the Poisson's ratio, and we know the value of M as lies between 3 to 4. That means 1 minus 2 by M is always a positive quantity. Okay. So that means when in X directional stress is 0, Y directional stress is 0, and Z directional stress is 0, that means from this formula this becomes 0 and this total becomes 0. That means volumetric strain is 0. That means at a steady condition, if no load will be applied on the block, that means there is no stresses will be available into the block. In that condition, there is no change in volume. Okay. Now we'll see as unidirectional stress. Okay. So that means we have considered here a rectangular block, and this will be subjected to the tensile stress in X direction. When tensile stress is developed in X direction, there is a change in the longitudinal direction, that in the longitudinal strain will be developed. That longitudinal strain will be positive one, but if you see this block, when tensile stress will be developed in X direction, there is also change in volume because lateral direction dimensions will be reduced. Okay, so that means the strain in X direction as sigma X by E because it is tensile one. But in Y direction, suppose we consider this is X, Y and Z direction. So this is in Y directional strain, as E of y is equal to minus sigma x by me, because so there is elongation reduced in the dimension in y direction due to the stress sigma x. So this is compressive one, that is it is a minus 1. So similarly in the z direction also E of z is equal to minus sigma x by me. Okay. Now we'll see the bidirectional stress. Okay. So for that we have taken here the x and y directional stresses on the block. So in x direction there is a sigma x stress, and in y direction there is a sigma y stress. Okay. So first we see as elongation, when these two stresses will be developed, so there is a change in volume will be available, okay, in all the directions. So what do we have? So E of x, change in strain in x direction is equal to sigma x by E. This is tensile one, minus sigma y by me. Okay, and so change in y directional strain, E of y is equal to sigma y by E minus sigma x by me. Similarly in z direction it is E of z is equal to minus sigma x by me minus sigma y by me, because due to the stress sigma x and sigma y, the z directional dimension will be reduced. So that's why this is minus 1. Now last one is the triaxial stresses. So for triaxial stresses we have considered a rectangular block. Just we have seen the derivation. This rectangular block is subjected to the sigma x stress in x direction, sigma y stress in y direction, and sigma z stress in z direction. So due to that the strain will be developed in all the directions, as E of x is equal to, in x directional strain is a sigma x by E minus sigma y by me minus sigma z by me. Similarly in y directional strain E of y is equal to sigma y by E minus sigma x by me minus sigma z by me. Then E of z is equal to sigma z by E minus sigma x by me minus sigma y by me. So here by using this one we can find out this volumetric strain, and from the volumetric strain we will see as change in volume. So change in volume from volumetric strain is equal to change in volume divided by original volume. Okay, so that means we can find out as change in volume as change in volume as EV multiply with original volume. Okay, thank you.